We are very happy to have you all here. To begin, I'd like to introduce you to the Director of UCAR's Community Programs, Bill Kuo.
Welcome, everyone. We are delighted to have you attend the CPAESS Discovery Seminar Series. This series began to share the impressive breadth and depth of the research from CPAESS scientists who study the entirety of the Earth system science. We have scientists who do everything from exploring our ocean depths to flying into hurricanes to take critical measurements to modeling coronal mass ejections to those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR UCAR community, and our many colleagues at universities around the world. We are using Slido so that you can pose questions for our speaker, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. Do not panic if you do not see your questions popped up, as we will be holding questions until our speaker completes his presentations. Questions will be revealed later during the Q&A portion of the seminar. Now it is my honor and distinct pleasure to introduce to you today's speaker, Dr. Neil Jacobs. Neil is the Chief Science Advisor for the Unified Forecast System, UFS, an effort by the broad scientific community to develop a common open source modeling infrastructure that encourages collaboration and eases the transition from research to operations with the goal of improving NOAA's operational models. Neil was a former active NOAA administrator, has been a long-time proponent for the need of a unified modeling system to improve U.S. weather and climate forecasting skills. As a Chief Science Advisor, Neil's primary focus will be to foster the participation of the broad research community in the development of the UFS. Neil brings a wealth of experience to the role from both the public and the private sectors, including working as a Chief Atmospheric Scientist for Panasonic Avionics Corporation, and serving as acting Undersecretary of Commerce for Oceans and Atmosphere, as well as Assistant Secretary of Commerce for Environmental Observation and Prediction at the U.S. Department of Commerce. Neil will be speaking today on the Unified Forecasting System, UFS, whose framework spans the timescale from convection to global and from a few hours to seasonal and subseasonal. By enabling the application across these scales and making the code publicly available, the UFS can leverage advancement from researchers and institutions across the country. Please join me in welcoming Neil. Neil, please take it away. Thank you.
Thank you, Bill. Thank you so much for that introduction. It's a thrill and an honor to be here with everyone and to get you up to speed on some things that we've been working on with the UFS, and then also give you a little taste for the vision of where we're thinking about going with this, and then get into a little bit of the background on how we arrived at the community modeling aspect of this. So if I back up a pretty decent amount, going back to the Fair Weather Report. So back in 2003, there was this report that came out, talks about the roles of the public sector and the private sector and who does what. And what you can see down here at the bottom, if we sort of look at the value chain of numerical weather prediction, we've got global observations, quality control, data assimilation, all the way to products and services. And it used to be that the private sector was really sort of a value add industry on the back end. But if we look at this almost 20 years later, the private sector is involved in the entire value chain from start to finish. And there's two ways that this could work. One is a collaborative and one is a competitive And what we really want to do is design this in a way to have it be collaborative. So if I was to take this from, say, a public-private academic partnership perspective, there's a couple of sort of baseline rules that all of these relationships have to be successful. The first one is the partners have to have complementary strengths and appropriate resources. Obviously, if they're not resourced properly, it's not going to be very beneficial. And then an entire costing approach. And one of the things that is incredibly complicated, and I'll use NOAA's budget as an example, but every government agency is very similar, and very large businesses are similar too. The money comes from a lot of different directions to fund different programs and projects. And so when you try to figure out how much something costs to do, trying to trace backwards how much it costs to whatever particular funding line is incredibly complicated. And in order to decide how much, what is the value of something, you really have to understand what the entire cost of it is. You also need a competitive procurement process that has to be transparent. It has to be seen from the outside as a fair and objective process. And that's a lot easier said than done. Probably one of the hardest things that I've seen in the weather enterprise, though, is risk aversion. This is a real impediment to innovation. And if you look at this plot, you can see over here we've got your reduction in risk exposure. So sure, you can, as you increase cost, you can buy yourself out of risk, and you get into this zone where this is an acceptable risk. But you can also reduce your risk exposure by stripping out all of the bells and whistles, which are usually risky to implement in a certain system. So where these two lines cross, this is typically where you would assume the optimal cost benefit is. But where this acceptable risk crossover point is really could lie anywhere in here. And there's some sectors, for example, the private sector, which is more willing to take on risk. So assuming you have this public-private academic partnership up and running, you definitely want to have it structured so that the gains are proportionally shared, so that any one particular entity doesn't feel like they're putting in more than they're getting out of it. To do this, you obviously have to have a strong legal regulatory framework and also favorable and stable economic policies. And by that, I mean, you can have these if you structure it in a way that's transparent from the very beginning. In other words, don't change the rules as you're going through this. So what are some of the barriers to community modeling? Why hasn't this happened already? There's fractured internal strategy, and this goes with, I would say, not just with NOAA, but other government agencies as well, and fractured external strategy. So a lot of this has to do with the private sector competing with the public sector and sort of, whose role is what. And so going back to the fair weather report, that did a great job of defining the swim lanes, but it's so different now than it was 15 or 20 years ago, or even 5 years ago, that this is constantly going to have to be an evolving process where we're re-examining the roles and priorities and who does what. The other thing that I found really challenging when I was at NOAA, and I knew this long before I came to NOAA, it's probably not a surprise to anyone, is a very, I guess obtuse is a good word, procurement process for hard iron. A lot of times when you look at NOAA's budget, they end up buying and upgrading their computer system based on supplemental bills, which the money is fantastic. But the problem is with a supplemental funding, you can't have O&M. And when you look at, say, for example, ECMWF or UK Med, and they can actually plan further out in the future because they have a longer budget profile that they can look to versus ad hoc adding on to a system whenever you get a supplemental bill. It makes procurement a real challenge. On the flip side of that is cloud. I mean, cloud is not, it's a different procurement strategy because you're not just buying a asset and sticking it somewhere. You're buying a service. and you pay on demand. And sometimes you get better deals if you agree to buy a certain amount further out into the future, or you buy it at a certain time than at different times. So there's a lot of different advantages there, but if you don't go about it properly, you'll end up paying a lot of money. Another challenge that historically NOAA's had is there's a tremendous amount of expertise out there from visiting scientists, but without the proper security clearances, they can't log into a lot of the compute. So without that access, trying to get external PIs or someone going on sabbatical to say, hey, I'm going to work on this component of model that NOAA Weather Service is running, they would need security clearances to be able to log into the machine. The only way I figured out to get around that is actually move a lot of the code outside of the firewall. And so you would have the community model be external. So the development work is happening on hardware that is not owned and operated by NOAA. So that's one of the reasons, and I'll get into that a little bit later on why the community modeling aspect is interesting. Then there's some cultural challenges. We've seen these throughout the weather enterprise. Again, that was sort of the genesis of the Fair Weather Report, but there's still disagreement over who does what. And in general, there are challenges with the funding allocation process. So there's competition between government agencies, there's competition within government agencies, there's competition between and within universities. And a lot of this, on one hand, competition is really good. On the other hand, there are things that competition works as a disincentive to, and that's collaboration. The risk aversion is always going to be an ongoing challenge. I discussed this in my BAMS paper last year, and that is there is an incentive to improve, obviously, but there's also a larger incentive depending on where you are in that value chain of not to fail. In other words, there are probably at least 10 times as many articles about a blown forecast than there are about a really good forecast. So if the model totally nails the forecast, no one really cares. If the model blows it, it's all over the front page news. And if it blows it because you had a node failure, some system outage, or something went down, then it's even worse. So that type of negative exposure generates a tremendous amount of risk aversion. I've seen over the years that there's a lot of committees, there's a lot of overlapping of these committees, and it's interesting that the committees sometimes contribute conflicting input. So I think in the process of streamlining the forecast system, streamlining a lot of these committees is going to be very beneficial. And then also there's largely a lack of documented code. That's being changed now with the rollout of the UFS, but there still needs to be a lot more documentation and support. So let me back up for a second and tell you a little bit about how this started, because I think you'll find this story interesting. So back in the day, we had EMC here, and they had the operational code. NCO, the NCEP Central Operations, was in charge of running the production system. And if you were crazy enough to want to run the GFS, you just called up these folks and asked them. They would put it on an FTP site, and you could download the code, which was what I did a long time ago. And I took a team of several people, many years, to try to figure out how to run it, because it was hard coded for IBM AIX. There was no documentation. We finally gave up on porting it to Linux and just bought an IBM P series system and mimicked NCEP's hardware for several cycles in a row until NCEP went over to iDataplex, which was a Linux-based system. In which case, now that it had shifted over to Linux, and this was around 2015, that opened the door for us being able to port the code over to Microsoft Azure, which was a Linux-based cloud computing service. So why would we want to do this? I would say this article is an interesting one from CNN in 2009, referring to this as 10 years ago. So way back when Enron was around, they realized that you can make a lot of money off understanding what the weather predictions were going to be. And the hedge funds were pretty quick to sniff this out and determine that if on one hand, if you had a better forecast, you would have a lot of power in the weather futures market. But if you could actually run INCEP's GFS and produce a numerically perfect replication of what that model would show, but do it quicker. In other words, if you could show someone in the market with a 15, 20, or 30-minute lead time advantage, what INCEP's GFS would produce, in other words, what the traders in the market would see, you would have a tremendous amount of trading power in the market. And so this became very interesting to a lot of different people in the banking industry who wanted to figure out how to run the GFS. And that's how I originally got roped into this, was let's figure out how to run INCEP's GFS. Let's figure out how to run it, not just a better version, but also an identical version, but run it a lot faster, which actually became a software engineering challenge. So I did that for several years with the team. And then once we switched over to running this in Azure, we had the ability to spin up parallel runs on the fly. We would just call up the cloud service provider and ask for more compute. And what it meant was that we almost had an unlimited amount of research compute on demand whenever we needed it. So if we wanted to test a new idea, we would just spin up more compute nodes and test it. And if we had non-competing ideas that we didn't need to necessarily run one after the other, we could run them all at the same time. So I started getting calls from people at universities wanting my team to test out ideas in our modeling system because they knew it was an identical configuration to what INCEP was running. And I would always ask them, have you told INCEP about this idea? And it was usually, yes, we have, but they don't have enough research compute to test it. And so we would test it. And then I would go to INCEP and say, hey, we tested out this idea. You should check this out. It's showing some promise. And then it got to the point where EMC scientists wanted to test out ideas in the Panasonic system. And then I started talking to Bill LaPenta, and he said, you know what? It would be really cool if we could just figure out a way to make this like an official way of doing business going forward. In other words, put all the code out there for the community to use and let them test their own ideas. And then they can come back to us with results, because what EMC didn't want is just an onslaught of ideas for them to test, because they didn't have the compute resources. They didn't have the personnel. And to be honest, probably 8 out of 10 of these ideas didn't work. So you'd be wasting a lot of their time. So we sat down and on a napkin, this was long before I ended up at NOAA, drew this out with Bill LaPenta and Futing Zhang from Penn State at an AMS meeting, I think, of what this would look like if we were to refactor the code to sort of a hardware agnostic architecture, put it out there for the community, and let the community test their own ideas, and then come back to INCEP or EMC with the results. And this was pretty much where we left off, when all of a sudden a series of strange circumstances led to me being at the top of NOAA, and Bill came to my office and he's like, you remember that idea we were talking about? Let's do it. This is a photo of us standing down the hall outside of my office. That's me right next to the window on the right, and that's Bill right across from me on the left. He came to detail in my office, and we designed out what the UFS would look like if you were to make it a community model. And this was a photo of sort of the recreation of what was on that napkin on the inkboard in my office. And you can sort of see, going from left to right, there was the T-2 years where we are today, and then looking out 5 years forward. And you can see things in there like UCP and JCSDA, and of course T-2 years is the NIM and the FIM. And then looking forward, we've got this unified vision. Where are we going to go? And this was sort of how we envisioned a lot of this environment. Here's a version of the funnel. It's interesting to see things like the UFS Steering Committee and UMAC, and then the other agencies. I blurred out the names to protect the innocents, but I left the dollar signs next to them because this is truly a community effort that we're trying to design here. So going back to cloud HPC for a second. So let's take, for example, this parallel surge development. It would be so nice if you didn't have to worry about being constrained by on-prem HPC. In other words, you're waiting for someone else's job to finish before you can kick off your run. And this is largely what the Weather Service and OAR scientists are faced with. There's quite a long queue to run the jobs. And if you look at these two plots, so over here on the right, this is ECMWF. So this green at the top, that's their production system. And the blue is their research. So you can see here in between some of these model cycles, they have roughly a 5-to-1 research to operations compute ratio. If you look over here on the left-hand side, this is NOAA. So you've got the orange and the blue, that's WCAESS, the production system and the backup system. And then over here, you've got their research compute. Now, if you consider that just one of these versions of WCAESS is the production system, at best, the research compute is 1-to-1. If you actually consider the entire amount of petaflops, they actually have twice as much compute for operations as they do research, or I should say half as much compute to do research as they do operations. And this is not a healthy, sustainable position to be in. You really want to see this at a 5-to-1 or even 7-to-1 ratio. The interesting thing about virtual machines and cloud service providers is it's scalable on demand. So you could say this is X-to-1. Maybe at some points you only need 3 or 4-to-1. Maybe at some points you need 50-to-1. Really, that X is dependent on the price of cloud computing and how much, say, Amazon or Google or Microsoft has on offer. And I can promise you that the amount of compute they have on offer is far greater than NOAA's ever going to get. And it's cost per hour. So if it's interesting for things like reforecast, reanalysis. You don't necessarily need to run these things in real-time cycling mode. You can actually do it very, very cost effectively. We've proven that you can run this stuff in the cloud. It's not a technical challenge. There are still antibodies out there to cloud, and most of them, it's cultural. It's fear of the unknown. It's something different, but this is where the future is. But you do want to make sure that you keep things relatively vendor neutral. You don't want to get too locked into various tools so that any one particular cloud service provider can lock you into using only their particular architecture. So the community as a whole is going down this from two different paths right now. There's an aggregation of observations on the front end, and this is something that the WMO is looking at. It's a much more efficient way of sharing data than the GTS. And then on the back end, a lot of the cloud service providers are interested in taking the output. So there's a big swath of private industry that is just interested in downloading and post-processing and doing the value add on the back end. And the cloud service providers are interested in this because while NOAA and the cloud service providers aren't allowed to charge for necessarily the download of the information, they can charge for the processing of the information. And so having the opportunity to store that information there and charge for the processing is a very good business model for the cloud service providers. And it's also good for NOAA because NOAA gets a really good deal on storage. But what you don't want to do is find yourself in a situation where all of your observations are aggregated in the cloud, all of your output is aggregated in the cloud, but all of your compute is on-prem, because then you're downloading and uploading. And every time you move data from point A to point B, it wastes time and costs money. So really, where I think the future is doing this all in the cloud from start to finish. And I think there's a lot of opportunities, particularly on how fast and efficiently we can do some pre-processing of the satellite data, which really opens a lot of doors to forecast skill improvement if we can extract more value from those data sets, just because they're simply so large. So if we step forward, I'm at NOAA for about a year. Congress is put together and drafted Section 4 of the NIDIS reauthorization, which is the Earth Prediction Innovation Center. And there was a lot of debate over the word center because it's not brick and mortar, it's a virtual center. I actually thought maybe National Environmental Information Lab would be a better name, but no one was really impressed with the acronym. If you look here on A and B here, the language is almost spot on, leveraging the weather enterprise to provide expertise. So there's this understanding that there's this broader expertise in the weather enterprise that can help, and essentially enabling these scientists and engineers to collaborate. So removing those inherent barriers that I mentioned on that previous slide. And then we have creating a community global weather research model. And these three sections here, accessible by the public, meets end user requirements, and end user, there's a lot of different end users here. And running on public computers. So this would be external, located outside of NOAA's information tech systems, and utilizes whenever appropriate cost-effective strategies, including cloud-based computing. So it's all here in this authorization. So if we go back to what this sort of flow chart looks like, I'm going to build this chart as I go. So there's a lot of white space I'm going to fill in here. Instead of the old way of doing the FTP, we've got this new way, and here's Epic here, and we've got releases. So one of the tasks within Epic is to take the operational code and build it into a release and put it out on GitHub for the public. Now, there's a lot of things like workflow, dependencies, flags for compiling, and various things that would need to be built into this to make it sort of a hardware agnostic, community friendly version of the code versus what NCO would actually be running on WCAS or WCAS2. So if we look at this is a slide that I put together that was kind of a vision for Epic before Epic was even a thing. So if we look at the end-to-end community model, we really want to leverage external capabilities. A lot of this hinges on the NCAR NOAA MOA, which is really focused on bringing NCAR and NOAA together in a collaborative way to work on a common infrastructure. And then another thing is when you're trying to simplify the inset production suite, it's critical that there's a strategy for sunsetting legacy models. And this does drive some users crazy if they've hard-coded a lot of things on the back end that are attached to one particular modeling system or file type. There is a lot of resistance to turning things off, even if there's something newer and better out there. And, you know, I've always thought that the amount of money you would invest to sort of do some hand holding to help people transition to the latest and greatest would be less than the amount of money you would need to invest to maintain all these legacy systems. But believe it or not, it is not a trivial thing to just turn stuff off. And if you're asked to add more things and newer things and told you can't turn off the old stuff, and also told that your amount of compute is not going to increase, all of a sudden you're really squeezed. So as I was saying before, the cloud HPC is a perfect solution for on-demand parallel search development. This is relatively new. It didn't used to always be this way. It used to be that the limiting factor with cloud compute was either you didn't have remote access to memory, or the interconnect architecture was not quite the same, and it wasn't as scalable. But now the cloud service providers have come up with architecture that's very NWP friendly, and really leveraging external and international expertise. So you don't have to worry about getting people security clearances or login credentials. You can just move all of the entire development sandbox to an external system where they have access to. One thing that I'm going to talk about a little bit is how you actually formalize this research to operations funnel. So we've been talking about the funnel for years. and actually figuring out exactly what the process is and how it works is one of the challenges that I'm going to be dealing with over the next year or so. So we do start with the GFS, or the medium range. Like I said, this slide was from 2018. So there's the medium range UFS app. Now there's the short range. There's one of the reasons why I thought it'd be good to start with the GFS was that provides boundary conditions to other models. It also, there's a lot of other models that would use that for initial conditions, and then also like hydrologic, biological models, all sorts of other things are kind of dependent on that. So start with that as the core and then work out. But we definitely want to look at all of these other Earth systems models as we move forward. Another thing that I really like about this external sandbox and moving a lot of the development into the private sector and elsewhere is you can allow to do sort of risky stuff. You don't necessarily need to be as afraid if you're going to do some development work and break something. So the UK Met actually has like a skunk works type division that I've really looked to over the years, and they basically have scientists that write proposals, and they'll get to go off site to this other facility down the street and test out their ideas. One of the things that I did want to keep continuity on, and this is something that Bill LaPenta really sort of hammered home with me, was that we need to accelerate the strategic implementation plan. So if you look at INCEP's strategic implementation plan, it's fantastic. The only thing that I would like to change is to try to do everything in there faster. And then of course, anytime you have a funnel with gates and stages, there's going to be a need for governance and decision making so that everything is agreed to in advance. And if this is up and running and functional and producing what we expect it to produce, it's going to generate a lot of confidence, both in the community with the users, but also Congress, which is where a lot of the investment ends up coming from. So we take a look at the UFS. So this is referred to as the rainbow diagram. So right now, INCEP is in this moratorium, and they've got this in place here because they're in the process of changing over their hardware for their operational system. But the take-home message on this slide is the unified forecast system is one of the goals is to simplify the production suite. So you've got all these models over here, and as you go out over here into the future, you can see that these same requirements are handled by less than half the number of models. And even though it's less than half, which is fantastic, it's even more efficient than that if a lot of them are using common code base, similar libraries, and similar workflows. The code is out on GitHub. I know that these screen caps are a little bit old. There's been a lot of work and a lot of updates, but you can go look at the GitHub for UFS and find pretty much all the code, but the applications out there. But just putting it out on GitHub is not necessarily enough. So back to the diagram here, we've got this flow chart. So we have the releases, they're configured to be largely hardware agnostic, put it out on GitHub, and then here's the community. And then magically out of the community come innovations and testing of new ops and everything else. I'm kind of joking when I say magically, because there's going to be a tremendous amount of funding that needs to get pumped into this section to make this part actually happen. But what happens when this happens? We have innovations, maybe we have private industry with new observing systems, and they want to test it out. I've always thought it'd be interesting to give the data assimilation and NWP to those in private industry who wanted to sell observations and say, why don't you optimize the DA system and test the impact of your own observation yourself, and then come to us with how great the answers are instead of expecting EMC or INCEP to run all the tests. But this brings us to a problem, which is what happens when the community comes back with all these innovative ideas. Well, this isn't anything new to anyone either. This has been around for a while. This is the RDO Valley of Death, which is how do you go from research to operations? And what I believe is the original version of the funnel in a paper. Is an internal NOAA document. And Sandy McDonald was the first author, but the design of the funnel is largely credited to Louis Uccellini. But this was a 2006 document. This is the first figure in there. And it's over the years has remained largely unchanged. I think this is a really great way to look at it. But there are some differences in the funnel, and that's, the research partners aren't necessarily who they were back in 2006. You got a lot of folks in research and private industry and elsewhere. And the other thing I would change here is the timeline. In my perfect world, I would just change these years to months and be done with it, but that's probably over optimistic. So we've got this funnel, and it's intentionally designed to be partially out of EPIC because we've got a community sandbox out here, and we've got stages and gates. Now, these stages would be different versions of testing, and if you want to get to the next stage, you have to go through the gate, which is some sort of set of predetermined requirements. And let's just say, at a very high level, the first one is do no harm. Does your innovative idea actually improve it? If it does improve it, does it break something else? Does it? And then as you get further down in the funnel, you move away from probably largely a scientific view and test to more of a software engineering optimization stability aspect of this. And each one of these stages and gates gets you to the next level, where it goes in the direction of more of a parallel production type testing of the idea. But how do we make this sort of a formal funnel? So we've got these initial baseline requirements, which are, you got to have a cool idea that does what you think it does, and then hopefully it doesn't break a bunch of stuff in the process. When you get closer to the bottom of the funnel, the research side really needs to understand and appreciate the constraints of the operational community. And that is where it really gets into code stability, because you can't just go out there and be crash and runs all the time. And then there's got to be, throughout this stages and gates process, there's got to be an objective. And this may seem obvious, but probably wouldn't be surprised that it hasn't always been this way. This is why the UMAC, the UCAC and Model Advisory Committee came up with this evidence-based decision. So what I would like to do is make sure that we all, just as a community, agree on what these stages and gates are ahead of time. So that way when you go through this evaluation process, there probably will be winners and losers, but as long as everyone knows what they're being scored on and judged by ahead of time, it's a fair process. So you get out of the situation of having to play favorites, or not invented here, or I put so much time into this code, why aren't you testing it this different way? Everything needs to be agreed to in advance in an open community framework. As you get further down, parallel testing obviously becomes more important, and ideally software engineers would be brought in through all of the stages. So you don't just come up with a bunch of code written by scientists and then throw it over the fence to some software engineers and have them try to figure out how to debug it and optimize it. So here's a sort of a view of what I envisioned the funnel looking like. So this is a figure from my BAMS paper, and I intentionally drew this with things like observations and software optimization and tools. So it's not just your classic model components, but other stuff that you would want to test in the community as well. And you can follow this through, where these are different stages. These are evidence-based, as UMAC says, gateways to get to the next level. And let's say, for example, there is an interesting innovation, but for some reason it doesn't meet the requirements to get to the next stage. Well, it's still valuable. And we'll talk about what you can do with this valuable but non-operations candidate here in a little bit. But at some point, as you get closer down this funnel, there needs to be a determination of, this is something that is of interest to INSEP an EMC and is an operational candidate, because there's a lot of innovative code and ideas and things that the research community would want to see that the operational forecast community doesn't necessarily need or want in their modeling system. And then as you get further down here, it becomes less of science and more of optimization and efficiency and stability. And even down at this level, when you're doing a lot of parallel testing, you'll find issues, biases, and other things that need to be worked out. So if we go back to transitioning to operations, at the very bottom of the funnel, there's something that's been in the works now for a couple of years called the RDO project. And this is largely NOAA-funded work that takes an innovation from the community or one of the labs and dedicates specific funding to transitioning that, whatever it is, into operations. And the challenge here is a lot of this funding comes from supplementals. So we're trying to figure out a way to retain a lot of this functionality, but not necessarily have it depend on how much money is available based on a supplemental bill. But maybe in a better world, it would be funded out of the base budget. But we get further down the funnel. At some point in this decision, it's a go or no go as to whether or not it's going to be something that is considered a candidate for putting into the production code. If we put that other funnel next to this, you can kind of see where these two align. You're coming in here from external community observations code, any random idea, and then you get down to this decision point, which you can kind of see this would be more of like the RDO project work, which is very NOAA-centric. Up here is more of the community work. And if we take what we see here with these on-ramps and off-ramps on this side, we can kind of draw that over here. So let's say, for example, pretty early on, we get an innovative idea, but it doesn't meet certain criteria, and it needs more research. This could get kicked back to the scientific community to continue to work on more development on the science side. If we get further down here, maybe it needs more work. Maybe it just needs to be more efficient at playing well with other pieces of the code. Maybe it just needs to be debugged a little bit more for stability or scalability. And then maybe there's something that is of interest to the research community. I can envision like idealized tests, diagnostics. There's a lot of various things in WRF that I've always used as a researcher that are never used in operations. But it would be great, and the research community would probably be very interested to have these bells and whistles bundled into the next releases that get put out on GitHub for the research community. So a lot of times you would have situations where these various tools that the research community wants to see in the code are added to the releases, the community uses it, and maybe as you get further down in here, it doesn't necessarily get put into the code that goes into operations. If you want to learn more about this sort of open innovation funnel, you should definitely take a look at Googling open innovation. There's a lot of stuff on YouTube, on the internet. It's pretty interesting, and it's used in a lot of different industries. One other thing I did want to touch on is the real-time observations. If we're going to get to a point where we're doing parallel development work, it's really got to be an apples to apples. So we need to have access to the real-time observations that you can tap into in the cloud-based framework to do this testing. So if you're looking at the impact of an observing system, or you want to test something, it's as apples to apples as it can be with the production system. So real quick, talking about some of the UFS, the matrix and the roles, this is a way it's structured now. For the most part, this is probably going to be the way it looks going forward in the future, but we've got these applications here. You can see short range, space weather, medium range. And then we've got these, the technical oversight board, the UFS steering committee, and these cross-cutting teams. So some of them are looking at, say, architecture, verification, validation, and then other ones are looking at ensembles, dynamics, land. A lot of these working groups are cutting across all these different applications because they intersect all of them. So this is largely the way that the UFS is structured, as a way that the different experts interact with each other. If we go back to this example, there are some decision points coming forward. So we're going to need community input on what is the exact criteria for these various stages and gates. And this needs to be agreed to in advance. The other points are, we're going to need community governance up here, because there's going to have to be some decisions made at some point about what even gets into the funnel or what gets tested. So the external community is going to have to come to whatever this deciding body is with at least some initial set of results or answers. And then down here, there's got to be more of a NOAA-centric governance to decide, is this something that is of interest to NCEP and NCO? And if not, is the research community interested in? Well, then maybe there's an off-ramp here where it gets bundled back into the next release. So what's in it for NOAA? You get to leverage a lot of the external expertise in the broader community. It streamlines the RDO process, ideally in a transparent and objective way. We simplify the production suite in the process of doing this. And when you focus on making the code as hardware agnostic as possible, it really commoditizes the compute, which drives down costs, because the cloud service providers or other compute manufacturers have to compete against each other. The private investment ends up being aligned with the public mission. So you avoid a situation where private industry is competing with the public sector. And you remove that sort of us versus them, which has plagued some of the weather enterprise in the past. The community engagement and outreach with this actually doubles as a training and recruitment tool. So this is something that I think is of great interest, well, for private industry and public sector. You know how to run the model, you're familiar with this. If the private sector ends up seeing a tremendous amount of value in this, they're obviously going to be big advocates for congressional support. And it also balances the risk burden. So it's taking a lot of that risk off of NOAA, off of the public sector, and spreading it out across the private sector, who's largely willing to take on more risk. And what's in it for academia? Researchers can contribute directly to the operational system. I know that a lot of research out there want to write papers, and other ones it would be thrilled to just have their innovative idea part of the operational forecast code. Experiments can be done in an apples to apples way using the production code. The funding opportunities simultaneously benefit research, education, and public, which I think is pretty slick. The community, the collective community, offers support for getting things up and running. So once you can see this on GitHub right now, people are posting questions, and they're answered by other folks in the community. Hardware agnostic code, again, it's user friendly, it's inexpensive to run. It doesn't get you locked into certain type of high performance compute architecture, which can be subject to cost run-ups. And the cloud HPC is really, it's a great way to handle fluctuations in demand. So if you're running an operational system, yeah, whether you go cloud or on-prem might be a wash as far as cost if you're running it at 98% capacity 24/7. But on the research side, when your experiments are kind of fluctuating based on what you want to test, cloud is a very, very cost-effective way to scale it out. Basic research and applied research uses the same code base. So this not always been the case. And there's been some reluctance on the NSF side to fund what they would consider applied research, because obviously that's not necessarily part of their mission. But if we're looking at the same code base for code that's both used for operations, but it's also used for a research tool as well as an educational teaching tool, it ends up potentially being a win-win. You get multiple entry points, as when I was describing that funnel, there's off ramps and on ramps based on the criteria. And another great aspect of this is now FAR nationals can work on production code and not have to wait for a lengthy 1 to 2 or more years process of getting a security clearance. And it doubles as a research and teaching tool. So if you're in academia and you're interested in using the UFS, say some sort of toy model configuration as a teaching tool, you can run it on a laptop. You can teach NWP to your students. And it's no longer a daunting mess of really complex code that you need a massive supercomputer to run. And what's in it for industry? So better forecasts mean better products and services. Obviously, for the weather enterprise industry, that's a great thing. But any industry that's weather sensitive, and I probably pretty much industry that you think of has a weather sensitive component, this is going to improve their products and services. Again, if you get to where your code is largely independent of hardware type to some degree, you can set it up so that the hardware manufacturers and cloud service providers have to compete for your business, which is going to drive down the operating costs. Putting the code out there does allow for additional configurations. So if you're part of the weather enterprise and you're not just downloading NCEP output, but you're actually running your own models, you can do much greater configurations and optimization and custom solution for your business clients. Government investment spurs innovation. Now we all know that, but what we really want to do is make sure that it spurs innovation that's consistent with where the market direction is going. And by that, I mean, the weather enterprise is not big enough to drive certain type of compute architectures. That's driven by, I don't know, the video game industry or the telecom industry or something like that. But if we can get in alignment with where the broader high performance computing, exascale, quantum world is going, the alignment makes a tremendous amount of sense. Otherwise, the NWP community is going to be out on an island by themselves somewhere. Better forecasts mean greater cost avoidance. This is true not just for the weather enterprise companies, but almost any company, whether you're in transportation, logistics, whatever. If you have access to better forecasts, even if you're just using the free and open available public forecasts, your cost avoidance is going to be very beneficial to your bottom line. Again, competition drives down cost to compute, rapid innovation. The indirect economic benefits will go well beyond the enterprise. So one of the things that I've always wanted to try to figure out is we got a pretty good idea of what the fluctuations of direct impact are, but what are the indirect impact? I think that number is huge. So what's next for UFS? Short term, map the process. So I kind of just took you through a mapping of what the flow, I would refer to it as a business model. What would the flow of this process look like? And then once we agree and figure out that's the most efficient way for ideas to sort of flow through the process, where do we need to put the community governance? We don't want to generate unnecessary governance where it's not needed. So where are the decision points that need governance from the community input, fair and transparent decision making, and just implement that only where needed. We need to deploy a really significant amount of outreach and training. So just putting all the code out on GitHub is not going to do anything. We need to get the community trained on how to use it. And I realize that that's going to require a fair amount of work, because when you just look at the code, it's a little bit daunting. But doing some hand holding, some training, some outreach, and getting people really familiar with this, because it's actually a lot easier than you would think it is. It's a lot easier than MM5. It's a lot easier than WARF, but there's still a fear of the unknown that we need to overcome with outreach and training. And then in parallel to that, develop teaching material. So doing a lot of outreach as for the UFS as a tool for educational purposes. Medium range, looking to solicit academic input to solve some key challenges, deficiencies in the model, things we're seeing, who out there in the community's got some ideas on how to fix these things, explore potential joint ventures with industry, maybe funding match opportunities with nonprofits. look at a lot of these different things like toy models and idealized cases that we would want to build into the releases of the UFS that are really aimed at the academic and teaching community. And then, of course, expand out beyond the current suite of applications into other aspects of Earth system modeling. So two last things I wanted to touch on before I wrap up here. The first one is a graduate student test. So this was originally initiated just as a way to sort of gauge how user-friendly this is. So you can get the code, run the code, change the code. How complicated was it really for your average graduate student in atmospheric sciences, not necessarily your average graduate student in a computer science department. And getting a lot of feedback from them on what their user experience was like. There are some workshops coming up. So the first one, I don't know if it's filled up yet. The cap is only 50 people, but there will be more. So these are workshops of essentially running the application in the cloud. So through the EPIC program, the compute time on AWS will be covered. You'll be given an advanced packet on how to set up an account free of charge. And this workshop run virtually through Zoom will take you through the process of deploying the code and running it on AWS. And you can see, based on the fact that it's scheduled from 11 a.m. to 3 p.m., that they're pretty optimistic that you can get all this done in a couple hours. So I'm excited to see this. There looks like there's going to be a tremendous amount of interest, so I can envision several of these occurring, but this is the first one, and registration is open for it right now. And lastly, I did want to plug the summer workshop. So Unifying Innovations and Forecasting Capabilities. It's July 18th through the 22nd in College Park. I will be there. This will be where we're doing a lot of discussion on what that governance structure looks like. So agreeing on the process, gaming out how we want the governance structure to look like. So if you're interested in having a say in the governance and how we design this, please register. And it's a hybrid workshop, so in person, but we also can do virtual. But I want to make sure that we have everyone's input on this, because once we lock it in, it's going to be hard to change. So I want to make sure that everyone in the community is really happy with the way this looks first. Likewise, the week after this, there will also be a UFS and EPIC session at the AMS Summer Community Meeting in Boulder. So we'll probably be talking about it there as well. So that's all I had. Really appreciate everyone allowing me the opportunity to speak.
Well, thank you, Neil, for an excellent seminar. Now we are open to questions. So we have had issues getting HPC code, a note on AWS, often waiting hours or multiple days. Have you tested this at scale? I love additional independent data. This is from Brian Dobbins.
We have. I would probably want to learn more. So contact me. It's in Jacobs at UCAR.edu, what you mean by at scale. And for GPUs, GPUs are a little bit new to a lot of this code compared to CPUs. There are different flavors of AWS as well. And one of the things that I've found is it depends on what type of architecture you're looking for as to the availability. And also on the AWS side, a lot of the sysadmins over there, some are very, very familiar with this NWP type architecture, and others are not. So you'll definitely want to get connected with the people over there who understand this.
Okay. Similarly, any public UFS crowd cost analysis available? There's broad agreement that crowd is much more expensive than on-prem HPC for high user use centers.
Well, that goes back to what I was referring to initially as your entire costing approach. So a lot of times on-prem doesn't include the entire cost of, you got to consider rent on the floor space, cooling, power, there's all sorts of other things that go into just what goes on and how much it takes to run an on-prem system. So you really want to make it an apples and apples comparison. The other aspect of cloud, and this goes back to scalability, there are some cloud architectures that scale much better than others. And if you're paying like on a node per hour time, if you're on an architecture that doesn't scale very well, you end up having to spread your job out across a lot more nodes, and it really ramps up the cost quick. So choosing the right architecture is key to making sure you get the best bang for your buck, and also your run times. And I don't mean how long it takes to run. I mean, when you run this on wall clock time, like if you've got experiments that don't necessarily have to be run on any particular time cycle, you can kick them off to run at goofy hours at 3 in the morning or on the weekend and get cloud for pennies on the dollar. And there's actually brokers out there who, for a small fraction of a fee, will queue up your job and kick off your runs at whatever cost threshold you want it to run at or below on. It's an interesting business model that I hadn't thought of.
Any other questions? So Neil, I have a question for you. As you know, over the past couple of weeks, they've been noted that GFS is making bogus hurricanes, and it's the European Center is model did not do that. So using this as an example, how do you see that this UFS community engagement could contribute and support the improvement on the model?
Oh, well, so this is something I think would be a great use case example, and a very simple one. But if you wanted to test out dynamics or physics or something like that, so let's have a working hypothesis that maybe it's not related to data assimilation, and you could just initialize some runs from an analysis file. You could test out various things by doing, changing configurations and such to sort of see, well, can I get it to go away? I mean, the first thing I would want to do is say, can I replicate it? And if I could, then does it have to do with something with the vertical level, number of vertical levels, the distribution? Is it related to the physics as a function of that? It's most likely these types of things are a combination of changes. And it's some of it's art and some of it's science, but it's great to have the community. You're essentially crowdsourcing everyone to look at this. So it's not just on 1 or 2 scientists at EMC who have 50 other things they're supposed to be doing.
Okay, great, thank you. Next question is coming from Will Sanks. You mentioned cloud being cost effective. How has this been tested? In my personal experience, the hidden fee caused the cost to be greater than expected.
There's no situations that I've seen where the cost came in less than expected. Let me put it that way. You need to be very careful about the hidden fees. So one of the downsides to cloud that there isn't a big advantage to on-prem, and I'm guilty of this myself, is debugging my code by kicking off runs and seeing where it crashes and going back and look at you try that stuff in the cloud and you're going to run up a big tab in a hurry. You got to read the small print, and there's a lot of different things, particularly when you get in a situation of uploading and downloading data to the cloud, where you can run up a charge pretty quick. For the most part, everything's in there. It's all written in the fine print, but you just got to make sure that you know what you're getting into, because if you're not, it can get really expensive in a hurry. So just be really, really careful. The best advice I would give is there are people out there in industry and even in academia who are all in the cloud now 100%, and they've probably learned all these things the hard way. I don't know that there's any type of online resource that tells you what to look out for, but there are people out there who know this stuff. So check with them. I think one thing that you'll find going forward is that the more cloud service providers start competing against each other for business, the more this stuff is going to disappear, because the competitors are going to point it out as a sales tool that is a reason why you should run it on their system instead of somebody else's.
Thank you. May I ask us a question? Hierarchical system development approach used at DTC to model development is efficient and useful in improving model components and consistent with your presentation. I think this is more like a comment.
I would completely agree. I'm a huge fan of this approach, and I think it not only is it great for development purposes, but it also allows for you to build in those early stage components like single column models and things like that that are really good for teaching tools.
Any more questions? Well, now it's we are kind of 4 minutes past the hour. I want to take the opportunity to thank Neil again for giving an excellent seminar. And please feel free to communicate directly with Neil if you have additional follow-up questions. Thank you, everyone. Thank you, Neil, for joining us. Bye.
Thank you.